currents and wires and whatnot, it would still vote. The corresponding clock would run the same. And if the clock involved nuclear reactions, ordinary nuclear reactions, to make it run, it wouldn't make any difference either. But it does make a little bit of difference. I'll come to what makes a difference in a minute, but the first possibility that may suggest itself to you, if you know anything much, you may have heard that it's possible to measure the concentration of sugar in water by putting polarized light through the water. If you put the piece of Polaroid that lets light through in a certain axis through the water, then you'll find in order to, when you watch the light as it goes through deeper and deeper sugar water, you have to turn the Polaroid of another piece of Polaroid at the other end of the water more and more to the right as the stuff goes through. Maybe it's to the left, I can't remember, but let's say to the right, as you go through deeper, deeper solution. And if you make the water light go the other way through the solution, it's still to the right. So there's a right-hand way, there's a difference for right and left. So if we put sugar water in the clocks and light, then if we put, say, in one tank of water and make the light go through and turn and put the Polaroid so it can just get through, and make the corresponding image on the other side, hoping the light would turn this way, it won't, it'll turn the other way, and it won't go through right. So by using sugar water, our two clocks can be made different. So it's a very remarkable fact. And it isn't true, therefore, at first that the two clocks will be, that the physical laws are symmetric for reflections. However, it's possible to make sugar in the laboratory. The sugar that we got that time might have been from sugar beets, but sugar isn't a complicated molecule. And it's possible to make sugar in the laboratory out of carbon dioxide and water and going through lots and lots of stages in between and make artificial sugar. When you put the artificial sugar in there, which is chemically and measured every way, it seems to be the same, it doesn't turn the light. Then, if you put bacteria in the water, in the sugar water, bacteria eat the sugar. And when you let the bacteria eat the sugar, and then try with what's left, it turns out first they only eat half the sugar, the artificial sugar. Second, when you're all done, it turns to the left, the stuff that's left. And now you find the explanation to all this is the following. And sugar is a complicated molecule, a set of balls, atoms, in some complicated arrangement. If you make exactly the same arrangement, but left as right, like if the arrangement is complicated like this, then you make one the same way. Then every distance between every pair of atoms is the same, in one as in the other. The energy of the molecules is exactly the same. And for all chemical phenomena not involving light, they're the same. But living creatures find a difference. The bacteria eats one kind and not the other. The sugar that comes from sugar beets is only one kind, all left-hand molecules. And so, or right-hand, and so it turns the light one way. The bacteria can only eat that kind of molecules. When we manufacture the sugar from substances which themselves are not asymmetrical, simple gases, we make both kinds in equal number. Then, if we let the bacteria eat, they'll eat the kind they can eat, and the other is left, and that's why it comes out the other way. It's possible to separate the two by looking through magnifying glasses at the crystals and separating them and so on, as Pasteur discovered, and so forth, so that we can definitely show that all this makes sense, and even our artificial sugar, then we can separate ourselves. We don't have to wait for the bacteria. But the interesting thing is that the bacteria can do this. Does that mean that the living processes don't obey the same laws of and so on? Apparently not. It seems that in the living creatures there are many, many complicated molecules, and they all have a kind of thread to them. One of the most characteristic molecules in living creatures are proteins, and it takes a little while to explain the details, but let's put it very simply. They have a corkscrew property, and they go, let's say, to the right. Now, as far as we can tell chemically, if we could make this chemically, the same thing to the left. It would not function biologically because it wouldn't, when it met the other proteins, fit the same way. That is, a left-hand thread will fit a left-hand thread, but left and right don't fit very well the same way. So the bacteria, having a left-hand thread in their chemical inside, can distinguish the left and right sugar. How did they get that way? Physics and chemistry cannot distinguish the molecules. It can only make both kinds, but biology can. It's easy to believe that the explanation is that in a long, long ago, when the life processes first began, some accidental molecule got started and propagated itself by reproducing itself, and so on until after many, many years, these funny-looking blobs with the prongs sticking out, yak at each other. But they are nothing but the offspring of the first few molecules, and then the accident of the first few molecules that it happened to form one way instead of the other. It has to be one or the other. So the thing that reproduces itself is either left or right, and then it goes on and propagates this on and on. It's much like the screws in the machine shop. Use right-hand thread screws to make new right-hand thread screws and so on. So this is probably one of the deepest demonstrations of the fact that the protein molecules are exactly the same in all life. They all have exactly the same kind of thread. It's probably one of the deepest demonstrations of the uniformity of the ancestry of life, the common ancestry of all life, and from back, in fact, to the completely molecular level. Now, in order to test better this question about whether the laws of physics are the same right and left, we can put the problem to ourselves this way. Suppose that we were in telephone conversation with a Martian or an Arcturian or something. We don't know where he is, and we would like to describe things to him. We want to tell him about things. We say, well, how is he going to understand the words? So that's been studied very much by Professor Morrison here. And he has pointed out that one way would be to start out and say, tick, tick, 2, tick, 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 3, and so on. And pretty soon the guy would catch on to the numbers. And then as you understand your number system, then you can write lots of numbers, and you could, for example, write a whole sequence of numbers that represents the weights, the proportional weights of the different atoms in succession. And then say hydrogen, 1.00, deuterium, and so on, so on. And he would, after he sat down with all those numbers and piddled around a while, would discover that the mathematical ratios were the same as the ratios of the weights of the elements, and therefore those names must refer to elements. And so gradually you could, in talking to him, to have a common language. In many ways, common. There are many. Now comes the problem. Suppose that he says, you fellas, after we get familiar with him, he says, you're very nice. Now I'd like to know what you look like. And you start out, well, we're about 6 feet tall. He says, 6 feet, how big is a foot? It's very easy, you say. A foot, 6 feet tall, is 170,000 million hydrogen atoms high. Well, it's not a joke. It's a possible way of describing 6 feet to someone that has no measure, assuming that we cannot send them any samples, nor can we both look at the same object. We have to tell them how big we are, we can do it. That's because the laws of physics are not unchanged under a scale change. So we can use that fact, to use the properties of the scale to determine, you can use that fact to determine the scale. Well, here we describe ourselves after telling us 6 feet tall and we're so-and-so bilateral on the outside and we look like this and there are these prongs sticking out and all this. And he said, that's very interesting. What do you look like on the inside? So we describe a heart and so on, and we say, now put the heart in on the left side. Now the question is, how can we tell him which side is the left side? By what possible, you say, you take beet sugar, see, and you put it, in water, and it turns. Only trouble is he has no beets up there. Or we have no way of knowing whether the evolution, if it was even corresponding to the same proteins on Mars as here, whether the accidents of the evolution would have started with maybe the wrong-handed threads. So there's no way to tell. So after much thought, you see you can't do it. And so you conclude it's impossible. However, about 5 or 6 years ago, certain experiments indicated that they got reduced all kinds of puzzles. I won't go into the detail. We got into tighter and tighter difficulties, more and more paradoxical situation, until somebody proposed, Li and Yang proposed, maybe the principle that right and left symmetry, that nature is the same for right and left, is not right. And that would help to explain a number of mysteries. And Li and Yang proposed some more direct experiments to demonstrate this, and I'll just mention the most direct of all the experiments, the easiest way to tell, was an experiment done. Well, there were several first experiments which were quite clear, but the one that's easiest to explain is this. Now, when we have a radioactive disintegration, in which an electron and a neutrino are emitted, for example, this is one that we talked about before, electron and antineutrino. Or this is a neutron disintegrating into a proton, an electron, and an antineutrino. Or the corresponding thing can happen to a neutron and a nucleus. Anyway, there are many radioactivities in which the charge of the nucleus increases by 1 and an electron comes out. The thing that's interesting is that if you measure the spin, electrons are spinning as they come out. If you measure the spin, you find out that they're spinning to the left. That is a definite significance, that the electron, when it comes out of the disintegration, is turning this way. And that helical description is a left-hand thread. It's as though, in the beta decay, the gun that was shooting out the electron were a rifled gun. And there's two ways to rifle a gun, because there's a direction, out. And then there's a question, do you turn it this way or that way as you go out? And the experiment is that the electrons come from a rifled gun, rifled, twisted to the left. And so, using this fact, we can call up the Martian and say, listen, take radioactive stuff. Now, I would have prepared a particular example, a neutron. And look at the electrons, which come from such a beta decay. And then you define left by this screw thread, and let's see, you let, it'll take me some while to figure out how to do it in detail. Say the electron's going up, and the direction of motion of the way it's spinning is into the body on the left side, and that's where the heart goes. Something like that. I'd have to think a little bit more of it. But anyway, it is possible to tell right from left, and thus the law of this, that world was symmetrical for left and right, has collapsed. Every conservation law has, well, the next thing I would like to talk about is the relationship of conservation laws to symmetry laws. We last time talked about conservation principles, conservation of energy, of momentum, angular momentum, and so on. Now we're talking about symmetry laws. It's extremely interesting that there seems to be a deep connection between the conservation laws and the symmetry laws. This connection has its proper interpretation, at least as we understand it today, only in the knowledge of quantum mechanics. Nevertheless, I will show you the following, that if I will try to explain the following, that if we will assume that the laws of physics are describable by a minimum principle, that the paths are taken so that some quantity is least, an idea I described once before. If we add that the laws of nature come from a minimum principle, then we can show that if the law is such that you can move all the equipment to one side, in other words, if it's translatable in space, then there must be conservation of momentum. That there's a deep connection between the symmetry principles and the conservation laws, but that connection requires that the minimum principle be assumed. You remember at one time we discussed one way of describing physical laws by saying that a particle goes from one place to another in a given length of time by trying different paths, and the actual path taken has this property, that there's a certain quantity, which unfortunately happens to be called the action, which is not to be taken to signify anything because it's got nothing to do with action. Anyway, there's a certain quantity called the action, which you calculate on this path. And if you will calculate it for any other path, the answer is bigger. It's least for the real path. And that one way of describing the laws of nature is to say that the action, a certain mathematical quantity, is least for the actual path than for any other path. Now, another way of saying the thing is least is to say this, that if you move the path a little bit, at first it doesn't make any difference. Suppose you were walking around in a wood, on mountains, on hills, but smooth hills, please. Smooth. The mathematical things that were involved here correspond to smooth hills. We're walking around on hills and valleys, and we come to a place where we're lowest. Then I say, if you take a small step forward, you won't change your height. When you're at the lowest, or at the highest point, a step doesn't make any difference in the altitude in first approximation. Whereas if you're on a slope, you can walk down the slope with a step. And then if you take the step in the opposite direction, you walk up. And that's the key to the reason why, when you're at the lowest place, taking a step doesn't make much difference, because if it did make any difference, if you took the step in the opposite direction, you'd go down. I mean, if it went up one way, it would go down the other way. But since this is the lowest point and you can't go down, in first approximation, the step doesn't make any difference. So we therefore know that if we move this path a little bit, in first approximation, it doesn't make any difference to the action. Now I want you to consider the following possible other paths. First, we jump immediately over to another place here nearby. Then we go along. This sticks out too far to make the diagram clear, so if you permit me to just change the shape of the path. Then we move on exactly the corresponding path to another point here, which is displaced the same amount, of course, because it's the corresponding path to this side. Now we have just discovered that the laws of nature are such that the action, the total amount of action going on this path is the same in first approximation to that path. That's from the minimum principle, when it's the real motion. Now I show you something else, that the action on this path is the same as the action from this little cross to that little cross if the world is the same when you move everything over, because the difference of these two is only that you moved everything over. So if the symmetry principle of translation in space is right, if that's right, then the total action between the crosses is the same as between the dots. But for the true motion, the total action on this cockeyed path here is very closely the same as for the original one. So subtracting equals from equals and so on and so on. Anyway, you could probably see, therefore, that the contribution from this little section and from this little section are equal. But in making this little motion, we're going this way, and making this one, we're going the other way. So if we make the contribution of this taken as the effect of moving that way, and the contribution of this thinking of it as an effect of moving that way, but taking it the other sign because it's the other way, we see that there is a quantity here which has to match the quantity here to cancel out, which is the effect on the action of a little tiny step to the x in the x direction. So there is that quantity, the effect on the action of a small step in the x direction is the same at the beginning as at the end. There is a quantity, therefore, that doesn't change as time goes on, provided minimum principle works and symmetry principle of displacement in space is right. Now this quantity which doesn't change is in fact exactly the momentum we discussed last time. A corresponding argument for the displacement in time, the delay in time, comes out as the conservation of energy. The case that if we rotate in space doesn't make any difference, comes out as the conservation of angular momentum, and so on. That we can reflect and it makes no difference doesn't come out to be anything simple in the classical sense, and it hasn't therefore got a simple classical interpretation, and people have called it the parity, and they have a conservation law called the conservation of parity, but those are just complicated words in the case of the quantum mechanics. All we're saying is that the right and left symmetry law is not valid, but I have to mention that conservation of parity because you may have read in the papers that the law of conservation of parity has been proved wrong. It should have been written because it's much easier to understand. The principle that you can't distinguish right and left has been proved wrong. Now I would like to say as we go on about other symmetries that there are a few problems, new problems. For instance, for every particle, like an electron, there's an antiparticle, a positron. For a proton, there's an antiproton. And we can make in principle, what we call antimatter, in which every atom has its corresponding anti-pieces put together. For example, a hydrogen atom is a proton and an electron. If we take an antiproton, which is electrically negative, and a positron and put them together, they will also make a kind of hydrogen atom, an anti-hydrogen atom, in principle. It's never been made in fact, but this is figured out that we could make this. And so we could make all kinds of antimatter in the same manner. Now the question is whether the matter works the same as the antimatter. And as far as we know, it does. And one of the laws of symmetry is that if we make stuff out of antimatter, it'll behave the same way as we make the corresponding stuff out of matter. Of course, if they come together, they annihilate, there are big sparks and everything else. And it was believed that this is true, that matter and antimatter have the same laws. Now the next question is this. Once it's found that the left and right is wrong, the left and right symmetry is wrong, an important question comes. If I look at this integration but with antimatter, an anti-neutron goes into an anti-proton plus an anti-electron, that's an positron, plus a neutrino, the question is the antimatter behave like the matter in the sense that it comes out left-hand thread, or does it behave the other way? And it turns out, we think up until a few months ago, that it behaves the opposite way, and that the antimatter behaves like the it goes to the right, where matter goes to the left. And so there was another principle, and in fact we really can't tell the Martian which is right and left, because if he happens to be made out of antimatter, he'll get the thing the other way, because when he does his experiment, his positrons are coming out, puts the heart on the wrong side. And so you can see that if you telephone the Martian and explain how to make a man, and suppose he makes one and it works. Well, let's make it, and he explained to him also all our social conventions and so on. Then when we go finally to meet this man, after he tells us how to build a sufficiently good spaceship, we go to meet this man and you walk up to him, and if you put out your right hand to shake hands, if he puts out his right hand, okay, but if he puts out his left hand, watch out, because the two of you... the two of you will annihilate with each other. These are all the symmetries that I have time to tell you about. I wish I could tell you about a few more, but they become more difficult technically to explain. And there are some very remarkable things which are the near symmetries. The remarkable feature of this effect that we can distinguish right and left is that we can distinguish right and left only with a very weak effect, with this beta disintegration. What it means that nature is 99.99 indistinguishable right from left, but that there's just one little piece, one little characteristic phenomenon which is completely different in the sense that it's absolutely lopsided, is a mystery that no one has the slightest idea about yet. Thank you.